In this lecture, we examine projectile motion where the projectile is launched from the ground at some angle. So when an object undergoes projectile motion, we know that the horizontal and the vertical motions are independent of one another, and that along the horizontal direction, the object covers the same distance each second because there's no acceleration along the horizontal direction, and the velocity remains constant along the horizontal. Along the vertical direction, we know that the object covers less distance each second on the way up and more distance each second on the way back down, because that's the way an object that is thrown vertically straight up would behave, and the horizontal and vertical motions are independent, so they're going to behave the same way they would if we just had horizontal motion or just had vertical motion. So let's go ahead and let's look at this particular projectile that's launched at some angle here with respect to the horizontal, and it has some initial velocity that's pointing along a direction that makes an angle with the horizontal. So there's some of this velocity goes into the horizontal motion, is causing it to be propelled to the right, and some of that velocity is causing it to be propelled upward. So we can take that velocity and we can break it up and say that some of the velocity is along the horizontal and some of it is along the vertical. And that arrow that was here, and I know I removed it in the simulation or in this animation, but that would have made a right triangle. And so the speed that that object was originally shot at could be determined using Pythagorean's theorem, so that that speed is just the x component squared plus the y component squared, the square root. And we're really not going to use that. I just wanted to point out that that's why we could figure out what that particular initial speed was. So in this case, I've got this projectile. It's launched off at some angle here. Some of that velocity causes it to go up, and some of it causes the object to move to the right. So after 1 second, the object is still traveling along the horizontal direction at a speed of 20 meters per second. But because there is an acceleration due to gravity acting down, the velocity in the horizontal direction has decreased by a factor of 10 meters per second. And then after another second goes by, the horizontal velocity is still 20, but the velocity in the vertical has dropped again by another 10 meters per second. And I can continue this. After another second goes by, again, the velocity in the horizontal is the same, but the vertical has decreased until it reaches the very top of its trajectory. So I know it's hard to see here, but the object is moving the same distance horizontally every second that goes by. So these balls along the horizontal here are separated by the same distance, but along the vertical, on the way up, the distance that the object covers is decreasing every second that goes by. At the very top of the trajectory, the object is still moving and it has horizontal velocity, but the velocity in the y direction or the vertical direction is exactly 0. And hopefully one of the things that you'll recall from the other videos is that when you shoot an object straight up into the air, its velocity after 1 second was 30, and then 20, and 10, and then it was 0. And so it's behaving exactly the way it would have in the vertical direction if you had just thrown it vertically. Now we can look at the motion as the object begins to fall back down. So as it falls back down, it's still traveling in the horizontal direction 20, but it now has increased its vertical speed to 10 meters per second, and the negative sign here just means that it's pointing in the downward direction. And after another second passes, the object is now traveling 20 in the vertical negative direction and still has the same horizontal velocity. And I can continue and I can draw all those in. So a couple of things that you should notice about this is that each one of these represents 1 second going by. So This is 1 second, 2 seconds, 3 seconds, 4 seconds. So it takes 4 seconds to get to the top. And then 5 seconds, 6 seconds, 7 seconds, 8 seconds. So the total amount of time in the air would be 8 seconds, and the time it takes to get to the top is 4. So there's still this symmetry in the motion. The time it takes to get to the top is the same as the time it takes to get to the bottom. And that should make sense, because if the object had been thrown vertically upward, that it would behave exactly the same way, and the horizontal and the vertical motions are independent of one another. We also notice that the objects have the same speed at any particular height. So if I come here to this height here and I go across, those two situations for the object going up and coming down, it would have the same speed because it has the same components along the horizontal and vertical. Both of these are 20 and both of these are 20. If I come down here, I have 20 in the horizontal, 30 in the vertical, 20 in the horizontal, 30 in the vertical. It's going down, but the speed would still be the same. So we still have that same symmetry that we had before. So this animation is just trying to again show you that the horizontal and the vertical motions are independent. So I have a dart, or I guess it's a cannon that's shooting a banana. And so it's shooting and it's aimed directly at the monkey, right? So it's aimed straight at the monkey. But as soon as that banana is released and shot at the monkey lets go of the tree. And so the banana and the monkey are both falling the same way vertically off of that straight line path that the banana had. If gravity wasn't present, it would follow a straight line, but because of gravity, it's pulled downward, and they're both pulled downward the same way, and that's why the monkey can catch the banana. This is just another picture. It's similar to that. Here, a person is aiming a dart, I guess, or an arrow at a coconut, and there's the straight line path. And so the dart would follow that straight line path or that arrow if gravity wasn't present, but the coconut is released at exactly the instant that the arrow is shot. And so after 1 second goes, I guess these are half seconds and 0.75 seconds, but the coconut is falling and the arrow is falling off of that straight line path the same way that the coconut is falling. So after a half of a second, the coconut falls a certain distance, and also the arrow falls that same distance. I guess we can't really see. So up here is the first distance. This is 0.25 seconds is where the coconut would be, and then here's where the arrow would be. And then after 0.5 seconds, here we go again. See, there's the time right here. The arrow has fallen down 1.5 meters, and over here the coconut has fallen 1.5 meters. And then after 0.75 seconds, the arrow has fallen 0.28 meters and the coconut has fallen the same distance. So essentially that expression for the distance is equal to 1/2 gt squared is appropriate for both how the arrow falls off that path and how the coconut falls. And so the person would hit the coconut. So we can use that graphical representation to describe projectile motion. So according to the picture that we just looked at, if we had a cannon here and we fired a cannonball, if gravity wasn't present, it would follow a straight line path. Now the way that we get the projectile motion is to realize that if we figure out where the cannonball would have been after 1 second, and we'll look at this in more detail in the next slide, then we know that wherever it would have been if gravity wasn't present, it falls off of that path according to the distance is 1/2 gt squared. And we've done this in previous examples. And so if I put in time of 1 second, 1/2 10 times 1 squared is 5, so it falls 5 meters off that path. and then after 2 seconds I go through the same process and it falls 20 meters and then 45 meters. And if I show that that's actually where the cannon would be, I can connect those lines and it shows that projectile motion. So let's see if we can do something similar to that. So I have an object in this picture that's launched at 30 degrees. And in this example, I have distances along the horizontal and the vertical. And my object has an initial speed of 60 meters per second. So what we would want to do is we would want to draw a representation of the object's position each second if gravity was not present. So this straight line path represents 30 degrees with respect to the horizontal, and it represents the path that the object would follow if gravity was not present. And then the marks on here, 1, 2, 3, 4, represents time intervals. So after 1 second, if gravity wasn't present, that object would be located on this line at this point, and then after 2 seconds here. And I know that if the object was traveling in a straight line and there was no acceleration and it was launched at 60 meters per second, that means it covers 60 meters every second, which means that the distance between each one of these dots needs to be represented by 60 meters. So the distance between the points has to be 60 meters. Now I didn't put all of them and draw them all in, but each of these needs to be 60 meters. And I'd have to figure out how to represent that on my graph. And I'd probably use a ruler if we were doing this in class, but just to show you this representation, this is what it would look like. Now we know that the object doesn't follow a straight line, so at any particular time the object falls from that straight line path according to the expression that the distance that it falls is 1/2 gravity times the time squared. So what we can do is we can determine the distance that it falls each second and subtract that from the position of the object on that straight line path. So one of the things that we need to do, and we're going to use 1 second intervals. In the picture with the coconut, the time frame was not 1 second. It was, quarters of a second, but it's the same process. So we just have to plug in for each of our times, 1, 2, 3, 4, 5, 6, and so on seconds, and figure out what distance the object would cover if it falls from that straight line path. And so we already did the first couple. So, and we've done this before, so 1/2 10 times 3 squared is 45, and 1/2 10 times 4 squared is 80, and so on, and we can keep going with that. So if we use that previous representation for projectile motion, we can now figure out how far it falls off of that path. So we have our distances here, and so at 1 second, the object has to fall 5 meters off that path straight down. My picture's a little bit messy, but you get the idea here that at 2 seconds, here was my straight line path from before, the object has to fall 20 meters. And after 3 seconds, it falls 45 meters straight down. These lines are not very straight, but that's because of trying to do this on PowerPoint. Straight down from point 4 should be 80 meters. And then after 5 seconds, it falls 125 meters. And then after 6 seconds, it falls 180. And now I've hit the horizontal. So I can now draw a picture that represents that projectile motion, which is just a line connecting those points on there. I notice that where it hits over here is the range of the projectile. So it started off at 0, and it hit here a little past 310 meters. So I'm estimating the range of the projectile, the horizontal distance that it travels to get back to where it started vertically. It started on the ground, ends up back on the ground, is 311 meters. I also see someplace up here that the projectile has reached some maximum height. And so if I go across on my graph, that maximum height is somewhere between 40 and 50 meters. I'm going to estimate the maximum height is right at 45 meters. And I could, again, if I had a ruler and I was drawing this, I could measure this distance here. But I do have my axes that I can use. So this is a sort of a graphical, conceptual way that you could determine where an object would land if it was projected at a particular angle. We would have to measure the angle, draw that straight line that the object would travel if gravity wasn't present. We would have to put these dots on here so they're equally spaced and that they represent the distance the object would travel if it was moving at a constant speed. So remember, these are all 60 meters apart. And then we would have to figure out how far it falls off of those paths. So regardless of your picture, these distances, 5 meters, 20 meters, 45, are always the same that it falls off of that path after each second. So the range, as we mentioned, is just the distance that the object travels horizontally as it returns back to the vertical position that it started from. So it started on the ground, ends up back towards the ground. And we measured that to be 311 meters approximately. It turns out there's also a formula that we could use to calculate the range if we didn't want to draw this picture to conceptualize it. And the range formula is tells us that the range of an object, and it has to start off and end up back where it started along the vertical. So if it's thrown at the ground, it has to end up back at the ground for this to work, is equal to the speed, this is the initial speed of the projectile squared, times sine of twice the angle. So in our case, the angle was 30, twice the angle would be 60, and then divided by gravity, where gravity is actually 10 meters per second squared. So our initial speed of launch was 60, our angle was 30 that we launched, and our gravitational acceleration is 10 meters per second squared. So if I plug in, I have to square the 60, sine of twice the angle, so this is going to be sine of 60 divided by 10 meters per second squared. And when I plug those values in, and I divide, and I can cancel out my units, I'll end up getting meters. So this meter will cancel out one of those, the second squared will cancel, and I get 311.7 meters. So my conceptual graphical representation for projectile motion is agreeing with the formula that I have for the range of a projectile. There's also a formula that describes the height of the projectile. And so the height, we can determine the maximum height as the speed of the object squared, where our speed is 60 again, times sine of that angle squared. This is a weird way to write it, but this just means take sine of the angle, which is 30, and then square that value, divided by twice the acceleration due to gravity. So let's try it and see what happens with our numbers. So the way to write this and put it in your calculator would be 60, and we'd square it, times sine of 30, and then square that quantity, and then divide by 2 times g. If I take sine of 30, I get 0.5. I still have to square that quantity, multiply it by, when I get 60 squared, 3,600, and then divide by, in this case, 20, and I end up getting 45, which agrees with what we had when we did this using the graphical and the conceptual representation for projectile motion. The way that we looked at projectile motion conceptually actually works if the object is thrown from the top of a cliff or a top of a building or at any given height, and if it's launched at some angle. So we would go through that same process. We just combine those motions. So essentially, you look at the straight line path that the object would follow. You figure out how much distance would be covered every second, depending on how fast it's thrown. And then you look at how far it falls every second based on that time, and then you can combine those results. So we're just doing the same thing for each of these, and these are different motions. In one case, the object is thrown up at an angle, and the other one it's thrown down at an angle. But again, the vertical and horizontal components of the motion can be thought of as completely independent of one another. A little bit more about the range of a projectile that's important. In this particular picture, the object is launched at various angles with no air resistance. The initial speed of launch is 50 meters per second. And there's a couple of things that we notice about this. First, you get the maximum range. So when it was shot at different angles, the maximum range is out here past 250, and that was the object that was launched at 45 degrees. So you're always going to get the maximum range when the angle is 45 degrees. The other thing we should notice is that we have two of the projectiles hitting at the same spot right here. And so that occurred, and also over here as well. So let's look at this one. This one's a little bit easier. So if I look right here, the two projectiles that hit the same spot was the projectile launched at 30 degrees and the projectile that was launched at 60 degrees. And so two projectiles that are launched from different angles at the same speed can actually hit the same position, and that occurs if the two angles add up to 90 degrees. So the 60-degree projectile and the 30-degree projectile both hit the same position, and they add up to 90 degrees. And if I do the same thing, I have another place over here where the projectile that was launched at 75 and the one that was launched at 15 both hit at the same spot. Those two angles add up to 75 plus 15 also adds up to 90. So any two angles that add up to 90 degrees will hit at the same spot, assuming that they were launched at the same speed. So are all of these, even if they hit at the same spot, are they in the air for the same amount of time? And of course the answer to that is no. So if I look at the 60-degree launch and the 30-degree launch that hit at the same spot, the one that was launched at 60 degrees is actually in the air at the same time. So if you fired a projectile at 50 meters per second at 60 degrees and 30 degrees, they both would hit the same position, but the one that was fired at 30 degrees would hit first, and then the one that was fired at 60 would hit second. So the information that tells us how long an object is in the air is the height. So the higher that an object has to go, the longer it's going to spend in the air. And that's because the horizontal and the vertical motions are independent. And we know that the time in the air, or the height that it's going to go, is dependent on the time. And so the higher it goes, the longer it's in the air. So in this case, this 75-degree projectile would spend the most amount of time in the air if they were all fired simultaneously, and then as the angle goes down, the amount of time spent in the air is less.